Welcome back to the video lecture series for the subject Deep Learning. In this video, we are going to cover Chapter 2 Deep Generative Models of Unit 5 Autoencoders and Generative Models. In the previous video, we studied autoencoders. What do? They take some input data, for example an image, they compress it into a small code and then they rebuild it back. The purpose there in autoencoder is to learn important patterns while removing unnecessary details. Now we step into something more interesting, generative models. Imagine you show a baby many pictures of cats. Over time, the baby doesn't just memorize each picture, but instead they start forming a mental picture of what a cat usually looks like. They learn the features of cats. Cats have two pointy ears, they have whiskers, they walk on four legs, they have a tail, and so on. So now, once the baby understands this general idea about a cat, baby or toddler can draw a brand new cat picture, one they have never seen before. It may not look exactly like any single picture you show to the baby, but it will still be recognizable as a cat. So it imitates cat. This is what exactly generative models do. They don't just store or copy the examples you give them. Instead, they learn the hidden patterns inside the data. And then they use those patterns to create new data that looks realistic. So they are not only about recognition, like saying yes, this is a cat, or no, this is a dog. They are also about creation, that is, making new real examples. That's why we call them generative models, because they can generate new things. So deep generative models are neural networks designed to learn and recreate distribution of training data. Now we'll see the functionality and major types. The best part is generative models are unsupervised learning. So no labels are required to learn. The model figures out the structure by itself. Generative models are used for visualization, abstraction, and of course generation. Famous examples include variational autoencoders and generative adversarial networks. So in one line, autoencoders compress and reconstruct, whereas generative models imagine and create. The earliest generative models is the Boltzmann machine. Think of it like a neural network where every node makes simple yes-no decisions. It is an unsupervised model, so it learns from raw data without labels. Its architecture has an input layer called the visible layer and one or more hidden layers. The neurons here are stochastic, meaning they don't always behave deterministically, they flip between states based on probabilities. So, Boltzmann machines are used to discover hidden features in binary datasets. And more advanced versions like restricted Boltzmann machines and deep belief networks built on this idea. Even though they are less popular today, they laid the foundation for deep generative modeling. So the types of Boltzmann machines are restricted Boltzmann machine, deep belief networks, and deep Boltzmann machines. Let's talk about restricted Boltzmann machines or RBMs. First, notice the term restricted. What does that mean? It means there are no connections inside a layer. The visible units don't talk to each other and the hidden units don't talk to each other. They only connect between the layers. This restriction keeps the design simple and avoids confusion in learning. Now, the connections that do exist are symmetric. That means if a visible unit sends information to a hidden unit, that hidden unit can influence it back in exactly the same way. You can imagine it like two friends giving each other equal feedback. What one says, the other reflects back. Next, RBMs use unsupervised learning. That means they don't need labels. We don't tell the model what is correct or incorrect. Instead, it looks at the data and discovers pattern on its own. For example, if we feed it shopping records, it might figure out that bread and butter are often bought together. Nobody explicitly taught it that. Finally, RBMs are energy based models. Each pattern of data has an energy value. Common patterns, the ones that make sense, are given low energy, so they are more stable and likely to appear. Rare or unusual patterns have high energy, which means the machine treats them as unlikely. So, in simple words, RBMs try to link low energy states with high probability patterns. Let's move to deep belief networks or DBNs. These are basically stacks of restricted Boltzmann machines, layer after layer. So the model learns features in a hierarchical way. The bottom layer looks at raw data like pixels. The middle layers learn higher level features like edges and shapes. The top layer understands abstract concepts like this is a digit 7. This layer by layer learning helps the network understand data step by step from simple patterns to complex ideas. This makes DBNs very powerful for feature learning and dimensionality reduction. They can also be used in supervised settings for classification and regression. So think of DBNs as an early attempt to build deep architectures before CNNs and GANs. They were especially important in the early deep learning wave around 2006 to 2010. Now let's understand the key properties of restricted Boltzmann machines, which are the building blocks of deep belief networks. First, no intralayer connections. This means that inside a layer, the nodes, that is neurons, don't talk to each other. The visible nodes, which represent the input data, are not linked to each other, and the hidden nodes, which represent the features being learned, are also not linked to each other. The only connections are between visible layer and the hidden layer. This rule keeps the learning neat and avoid confusion. The second property is directed acyclic connections. Now this sounds technical, but it's simple. Directed means the connections have a clear direction like arrows pointing one way. Acyclic means there are no loops. In other words, information flows in a straight, orderly fashion, no going in cycles. DBNs are formed by stacking RBMs, that we know, and the connections between layers are directed and acyclic. Information flows from visible to hidden layers in a directed way with no loops. Third one is non-linear transformation. RBMs are not limited to just straight line or linear relationships. They can actually learn complex non-linear transformations of the input. In simple words, they can pick up hidden patterns in the data that a normal linear model would completely miss. This ability allows RBMs to capture hidden structures in data. For example, while a linear model only sees handwriting as a grid of dark and light pixels, an RBM can actually learn features like strokes, curves, and angles that define a digit. This is why RBMs are considered powerful feature learners. Now let's talk about the applications. Dimensionality reduction. Suppose you have a data set with thousands of features like medical images. It's very complex. RBMs can compress this into fewer dimensions while still keeping the most important patterns. It's like summarizing a long novel into a short outline without losing the story. Next is feature learning. Instead of engineers manually designing features, RBMs can automatically learn them. For example, if you feed an image, RBMs can learn to recognize edges, shapes, and textures without you telling it what to look for. It's like having a smart student who discovers shortcuts and patterns on their own. Next is classification models. RBMs also play well with supervised learning. Once they have learned features from raw data, these features can be used to build strong classifiers. For instance, RBMs have been used to classify handwritten digits, like the famous data sets, or even more complex images. They act as a foundation, giving other models high quality features to work with. Here is one of the most revolutionary breakthroughs in AI, something called Generative Adversarial Networks or GANs. GANs can create brand new realistic data that looks just like the training data. Not just copying but creating. Imagine new human faces that look real, but those people don't actually exist. That's what GANs can do. So how does this magic happens? It's actually a very clever setup using two neural networks that compete with each other. The first one is the generator. Think of the generator as an artist. Its job is to create a fake data, maybe fake faces, fake handwriting, fake images, etc. But here's the thing, it doesn't start with anything meaningful. It just takes a random noise as input and tries to turn that noise into something that looks real. At first, the generator is terrible. Its output looks like some simple things, not real things. But as it gets feedback, it improves step by step. The next one is discriminator. Now think of the discriminator as a critic. Its job is to examine data and decide, is this a genuine sample from the real training data, or is it a fake made by the generator? So basically it's playing the role of judge. The battle between the adversarial training, the important thing is these two networks are locked in a constant battle. The generator keeps trying to fool the discriminator keeps trying to catch the generator. It's like a game. Imagine forger making fake currency notes. At first, the police can easily catch the fakes, but as forger improves, the police also sharpen their skills over time. Both sides become better and better. In the end, the generator gets so good at making fakes that even the discriminator struggles to tell them apart from the real ones. That's why this process is called adversarial training. The result of this battle is extremely realistic outputs. That's why GANs are so powerful today. They are used to create deep fake videos that looks shockingly real, generate AI art and paintings, create synthetic human faces that don't exist in reality, even in fashion design, furniture design, and game development. Let's now see how GANs actually train. The process is like a cycle where the generator and discriminator keep improving through competition. First, it begins with a random seed input. The generator takes a fixed length random vector. We call this the latent space, and from this it tries to create an image or some data. At first, these outputs look very poor. Second, next comes the discriminator evaluation. The discriminator looks at this generated images and asks this, is this real or fake? It compares it with real data from the training set. Then we have the discriminator penalty. If the generator's output is unrealistic, the discriminator penalizes it. At the same time, the discriminator also updates its own ability to catch fakes. And finally, generator improvement. The generator uses this feedback and tries again, improving its outputs step by step until they look more realistic. This cycle repeats again and again. Over time, the generator becomes so skilled at producing realistic images that even the discriminator finds it very hard to tell the difference between real and fake. And that's why we say GANs work like a game between a forger and a detective. The forger keeps improving the fakes while the detective keeps sharpening their eye, both getting better with each round. Now let's see some the types of GANs that researchers have developed to solve specific problems. First one is vanilla GAN. This is the most basic form of GAN. Both the generator and discriminator are built with simple multilayer perceptrons. So that's the basic neural networks. It works well for simple image classification but struggles with complex and high quality images. Think of it as a starting version of GANs. Second one is conditional GAN. Here we add extra information like class labels or categories to both the generator and the discriminator. For example, if we want the GAN to generate images of cats and dogs, we can tell it which class to focus on. This makes it much more powerful and controllable. Next is deep convolutional GAN. This was a big breakthrough actually. Instead of simple perceptrons, DCGANs in short, use convolutional neural networks, the same technology used in image recognition. With this, they can create high resolution, high quality images like photorealistic human faces. Next is CycleGAN. This GAN is used for image to image translation. For example, turning a picture of a horse into a zebra or converting a summer landscape into a winter one. It's widely used in style transfer applications. The last one is StyleGAN. This is one of the most advanced GANs. It can create extremely realistic and controllable synthetic images. For example, StyleGAN can create human faces that look so real you cannot tell they are fake. Even though these people don't exist, it allows fine control over features like hair color, smile, or face shape. So, with this, this session gets completed. We'll see in the next one.